So let's talk about some basics when it comes to graphing exponential functions. And we'll want to know these because what we're going to do is we're going to be able to graph a exponential function like this given the basic graph and using shifts in translation. So we need to know a little bit about this basic graph first. First of all, for all functions of the form f of x equals a to the x, where a is a fixed base, a greater than 0, but a is not equal to 1, we can say the following. F of 0 is equal to 1. How do we get this? Well, this is based on the rule that we looked at before. Any base raised to the 0th power must equal 1. So that's pretty good. For the second one, f of 1 is always equal to a. Well, that means that, of course, we're saying that a raised to the first power is simply equal to itself. Well, that makes sense. And, of course, by our exponent rules, this says f of negative 1 is 1 over a to the negative first, by definition, would be 1 over a to the first. So already we're just using our exponent rules when it comes to establishing some information about this function, but now let's take it a little bit further. What does this mean as far as the graph is concerned? Well, in the first case, if we're saying that f of 0 is equal to 1, we know that means that on our function right here, our graph must pass to the point 0, 1. This is a given point on all basic exponential functions, and it doesn't matter what your base is. My example here is y equals 3 to the x. So when we say 3 to the 0, of course we're going to get 1. This graph will also pass to the graph at the point 1, 3. And that goes along with our second piece of this, b, where f of 1 is equal to a, whatever the base is. 3 to the first is equal to itself. Then we come over here to negative 1. And what should happen there? Well, in this case, because we're letting the exponent be negative 1, we're going to get 3 to the negative first, which is 1 over 3 as our y value. And of course, that goes along with our rules from above. Letter C says 3 to the negative first would be 1 over 3 to the first. How about the rest of it? Well, we said in our definition that the domain of all exponential functions is x is in the set of all real numbers. Well, that's one thing. Certainly, we can see that if we were to put in any real value of x, we should get a real value out. If I put in 3 to the third, I know I'm going to get 27. If I keep getting larger and larger values of x here, I'm going to get larger and larger values of y. So as x tends towards positive infinity in this graph, it looks like y tends towards positive infinity. But how about that other end over there? Well, we can try substituting in some negative numbers and see what happens. And let's try that right now here. If we were to look at our graph for these exponential functions, we chose negative 1. We know we get 1/3. If we tried negative 2, we're going to get 1 over 3 squared, which is 1/9. So it's going to go down to 1/9 here. If we tried negative 3, we're going to get 1 over 3 to the third, which is 1/27. We go to negative 4, we're going to get 1 over 3 to the fourth, which is 1/81st, and so on. As we go further and further into the negative direction, these values tend to get smaller and smaller. They tend to go towards 0. So in other words, as we go to the left towards negative infinity, it looks like the y value tends to 0. But you'll notice that it never goes negative. We never get a negative number. We're just going to get smaller and smaller positive numbers. So we could say that as x tends towards negative infinity, our limit as x goes to negative infinity of 3 to the x tends to go towards 0. And that is the definition of a horizontal asymptote. And so we have a horizontal asymptote at y equals 0 as x tends towards the negative values right here. So there's only a horizontal asymptote on the left, not on the right.